All right, in the previous videos we've talked a little bit about electric force, and now what we're going to do is talk a little bit about electric potential energy, which is the energy associated with bringing charges together or sort of separating them. And we're going to do this just briefly by analogy because you've seen how this works when you have objects that interact gravitationally. So in terms of the gravitational potential energy and how that changes in going from taking a mass from one location to another, what you have is minus the integral from the starting location to the final location of the gravitational force dotted into the path that it takes. So the idea here from mechanics was we had some object with some mass, we have some other object with some mass, and we move that object around in the gravitational field of the other object from some location to some other location. One of the things that we learned in that case is even if the object takes this sort of squiggly path, what matters is just the initial location and the final location, right? This is this idea of potential energy, that we only care about the endpoints. And we're going to find that that's still true for the electric force. It's a conservative force and it still operates in exactly the same way. So the description that we're going to have for the electric potential energy is going to be minus the integral from the initial location to the final location of the electric force that acts on a particle along the path that the particle takes. And so the way that we're going to deal with this is we're going to actually do this by example. We're going to have a particle that starts off near another one. So here's Q1 and here's Q2, and they are separated by a distance we'll call capital R for the moment. And this is the initial state. In the final state, what we're going to do is we're going to take Q2 to be really, really far away from Q1. So we'll pull it out, essentially let it go really far away. And what we'll do is we'll let that distance go to infinity. And this will be the final state. And what we're going to want to do here is we're going to want to determine what is the associated change in the electric potential energy of the system of these two particles as a result of taking Q2 out to infinity. Now, there's an assumption that we've made here, which is that there is an electric force between these two particles. There's a force that Q1 exerts on Q2. And Q2 is the only one that's moving, right? So what we've done is we've glued down Q1 relative to the origin of coordinates, and then taken Q2 and taken it from some nearby location to some faraway location, okay? So the idea here is that what we can do is start from this description of the electric force, which we are looking at how Q1 acts on Q2. So Q2 will be our test charge, and E1 will be our electric field due to 1. So this is the electric force that goes in here, but really what this is actually is the force that 1 exerts on 2, right? Going back to our other description of it. So this electric field is the electric field description that we've had previously for point charges. So we'll just write the rest of that out. So that's going to be 1 over 4 pi epsilon 0 Q2 Q1 over r squared r hat. Now, we're making another simplification to this problem in that we're only going to deal with it in one dimension. And the reason for doing that is to make the mathematics a little bit simpler for us, but also to be able to sort of describe it a little more simply. So we don't really lose anything by saying this all occurs along the x direction, and then we only care about the x components of the electric field, and we can cast our integral to be a little bit more simple because we're moving only along the x direction. So in this case, what we've done is we've simplified the electric force to be a one-dimensional force, or to be described in one dimension rather, as the product of the two charges times x squared x hat. Now, the last thing that we're left to do is to sort of construct this integral, and then we'll take it. So in the bottom corner here, I'm going to write what that integral looks like, and then I'll erase this, and we'll do the integration. So the change in this electric potential energy associated with this system is then minus the integral from the starting location, which is capital R, to the ending location, which is infinitely far away, of 1 over 4 pi epsilon 0 Q1 Q2 x squared x hat dot dx x hat. because that describes how we're actually taking the path. That's where we're going, in a sense. So let's get rid of this, and we'll see that this cleans up a lot because both the electric force and the dl point in the same direction. So this cleans up to be an integral that is minus. We're going to take out all the constants to make things easier on us to see what we're actually integrating. The integral from r to infinity of dx over x squared. Right? So we can go ahead and integrate that. So we'll have this sort of overall minus sign out here. And we're just going to take this integral by itself. And what we'll have is minus 1 over x evaluated at r and at infinity. We can take out that overall minus sign from here and evaluate the endpoints. And what we'll have is 1 over infinity minus 1 over r. That is the change in the electric potential. As this goes off to infinity, this first term vanishes. And so what we find is that the change in the electric potential is Q1, Q2, 4 pi epsilon naught, minus 1 over r. So depending on the sign of the charge, this change in potential energy is either positive or negative. If they're like charges, it is a negative change. If they are unlike charges, it is a positive change. We can also describe the electric potential energy associated with a given position, right? Because now we have sort of a description of this r being any r. So in a sense, if we were talking about the potential energy associated with a given location or given separation between two charges, that electric potential energy is going to be 1 over 4 pi epsilon 0 Q1, Q2 over r. That'll be just the general description of it. There's no minus sign. This minus sign came in from the integral, not from the description of the potential energy. So that's the electric potential energy. That's how you go about calculating it. We're not terribly concerned with you being able to reproduce these kind of integrals and so forth, but to think through the concepts of taking two charges and sort of pulling them apart or bringing them together, thinking about the sign of the potential energy that's associated with that depending on the signs of the charges. So while we did go through the derivation, the idea is think about how it's set up, think about these kinds of thought experiments, and think about the resulting implications here.